welcome and thank you, Ludwig, for the invitation. Today I will talk about spatial network calculus and the performance guarantees in wireless networks. This is a joint work with Professor François Bacheli. Okay, this talk will be divided into two major parts. In the first part, we will introduce the techniques and tools towards performance guarantees in wireless networks. And in the second part, we will have concrete wireless models to illustrate how to get those performance guarantees. We are driven by this main question, which is it possible to have provable performance guarantees for all links in an arbitrarily large wireless network? And this is an illustration of a device-to-device network where there are links consist of transmitters and the receivers. And this is in the context of finding the worst case user performance, and also in the context of ultra-reliable and low latency communication. So what do we know about performance guarantees so far? In communication networks, there has been a development of this tool called network calculus towards performance guarantees in queuing systems. In brief terms, it relies on constraints on traffic arrivals and also on guaranteeing some service curve. For example, the well-known sigma rho traffic characterization. And on the right side, this is a figure to illustrate the concept of network calculus, where you have this arrival traffic curve and the departure traffic curve. And the main conclusion is you could have deterministic bounds on the delay and backlog of the queues given the predefined constraints. And there are stochastic bounds under different regimes as well. So what about wireless networks? We know that it is in the widely applied wireless models, it is impossible to get performance guarantees for all links. For instance, this is a Poisson cellular network where you could see the red circles are the locations of base stations, and the black curves are the boundary of the cells. And if you look at if you throw some users on this plan and look at their performance over a long period of time, on the right side of the slide is a figure of the distribution of the reliabilities of the links. So in this case, you could see a wide range of performance among those links. And the minimum performance of all links is zero reliability. It is also known that for Poisson type of networks, there is always a non-zero fraction of unstable queues. So why is this, in the wireless case, there is no such guarantee yet? The reason is that in the wireless setting, there is a variety source of uncertainties, including spatial locations of transmitters and receivers, and the nature of fading, shadowing, and the nature of the wireless medium that allows channel access, in addition to the randomness in traffic arrivals in time. And the type of guarantees we're interested in is to have minimum performance for all links all the time. So all the previous consideration lead to the idea of spatial regulation, which we call spatial network calculus, and it is about performance guarantees for all links in arbitrarily large wireless network. There are three key components in this network calculus, spatial network calculus, which are fault regulation, short noise regulation, and void regulation. We'll show that the first two types of regulations, they are designed to control the clustering of wireless links in a network. And moreover, Ball regulation is equivalent to short noise regulation. And the second class of regulation is the void regulation, which is designed to control the coverage of the network. Combining these two classes of regulations, we will show that service curves for all links is indeed possible, and they are of deterministic nature without fading, and stochastic nature in the presence of fading. Yes.
Will you explain later what is void regulation, more precisely what is a void regulation?
Yes.
Okay.
Yes. This is an overview of the main components here. Yeah, I will go through them. And also these regulations will be defined in the strong sense and the weak sense, where the former is in the sense that the regulation is defined for every location in the plan, and the weak regulation is designed for a set of observers specifically. Okay, so here's our first definition, Ball regulation. For a stationary point process defined on R2 on a probability space, we say that phi is strongly sigma rho nu Ball regulated if for all radius R, the number of points in this ball of radius R is upper bounded by this polynomial of degree 2. Almost surely. So this figure illustrates the idea of counting points in of a point process. The first thing we observe is that by stationarity, what we observe at the origin is observed everywhere on R2. So if you are centered at an arbitrary location on R2, you see the same bound, which is of this polynomial form. And secondly, we actually can prove that all the locations jointly see this bound simultaneously. Thirdly, this definition can be generalized to arbitrary dimension, including the one-dimensional case, which will give us a similar characterization of temporal traffic arrivals.
So just a question. I was wondering why it was a polynomial of degree 2. I think it's because we are in a plane, in fact, I suppose. Yes. And so if you are in other dimensions, then maybe it would be in 3 dimensions. Maybe we have something with a power of 3.
Yes.
Okay.
So it's with polynomial of degree d in the.
I did that.
Yes.
the last sentence. Okay.
Yes. So if you think about a stationary point process, it's proportional to the.
I didn't see it.
Okay, so we have this definition. Are there any point process that satisfy this kind of constraints? The good news is that yes, we can find such point processes, and a notable example is of hardcore point processes. And we prove the existence of such polynomial bound by connecting to severe packing. So hardcore point processes are such that where no 2 points within certain minimum distance coexist. And here we have an example of a hardcore point process with minimum distance of 2h between any pair of points. And we consider the points within the radius of within the ball of radius R. All the balls centered at these points must be contained within the ball of radius R plus h. And then we use the volume fraction occupied the balls in the densest sphere packing to obtain the bound here, which is the function that depends on the radius, the minimum distance h. Are there any questions? Yes.
Just how do you get just quickly how do you get this long?
So the question is to find how many points you can have within a ball of radius r, and to do that, you for every point you draw a ball of radius h around those points, and then the collection, the union of all those balls must be contained within a ball of radius r plus h, and you have this, and then you use the area fraction that gives you the maximum, the densest packing possible. Yeah. In fact, this bound is achieved by hexagonal type cells, triangular lattice. But this problem is in R2, it's circle packing in circles. And there are general results for general dimensions as well. And we have a key counter example, which is the Poisson point process that we mentioned very early on from the talk. In fact, the number of points within any ball of arbitrary radius r is Poisson distributed, which is with its mean proportional to the size of the region. And this cannot be almost surely upper bounded for any r. However, one can regulate Poisson point process, or generally any point process, by removing a small subset of points and make it hardcore. So if you have a hard constraints on the minimum distance between points, you will be able to obtain the polynomial bound. This particular type of thinning Poisson point process are known as the Martin hardcore processes. Our second definition regulation is called short noise regulation, and it will be clear in a second why it's called this name. Strong sigma rho mu short noise regulation is defined such that for all non-negative bounded and non-increasing functions L, and for all R on the positive side, you have that the total shots from it. So if you think about each point within a ball or radius r sending some signal to the origin, the total strength of that signal is upper bounded by the formula on the right hand side, almost surely. So it involves the integration of this function L. And if we let r goes to infinity, we get an almost a sure upper bound on the short noise, which is the summation of all points in phi, the summation of all the signals from the points in phi, which is upper bounded by this quantity that we denote by A of L. And the integral is when you let r goes to infinity. And secondly, if we take a special function, which is when L is equal to 1, we retrieve the sigma rho ball regulation. So if you take L of R equivalent to 1 here, you retrieve the condition on sigma rho ball regulation. In fact, you can show that it is not only a one-side implication. It is equivalence between short noise regulation and Bohr regulation. I will not give the proof here, but the main idea is to use summation by parts and the Riemann-Stieltjes integral. And what this equivalence tells us is that if a transmitter point process is sigma rho nu Bohr regulated, then the total power of received signal is almost surely upper bounded from any location on the plane. And so is the interference. The second thing is that in the definition, this function L is quite general. We require it to be non-negative, bounded, and non-increasing. And it is quite unique, which will be used in deriving stochastic bounds in the next slide. So we consider a stationary point process in R2, and each point is associated with a ID mark, which is denoted by h of x here. They are non-negative and has finite mean and satisfy the Kramer condition. And the theorem says that if the ID marks satisfy the condition and the point process phi is strongly sigma rho nu Bohr regulated, then for the conditional Laplace transform of the short noise, which is the quantity here, that will include the randomness from the marks. This quantity, the conditional Laplace transform of this quantity is upper bounded by the quantity on the right-hand side, which is exponential of A of L tilde, where L tilde is equal to the log of the Laplace transform of fading as a function of the L function.
Can you quickly recall what is the parameter?
It is that if you have some S star such that the Laplace transform of this random variable is finite if S is the absolute value of S is less than S star. We'll use so this result comes from the universality of the L functions used in our definition of short noise regulation. And using this theorem, we will be able to have computable bounds on the tail distribution of interference in the presence of random fading. So I will quickly go through the proof of this theorem, which is the only proof I have for today. So the left-hand side, the first equation is the conditional Laplace transform, and it can be written as the expectation of the product form of each exponential of the fading times the short noise from X. And thanks to the independence of the marks, we can write the expectation inside of the product. So we have the product form of all the Laplace transform that is of the fading random variables. And then we rewrite the product form in a form of summation using a basic transform. And we recognize that on the inside of the exponent, it is a form of short noise, only that this function L is transformed into a form that is that involves the Laplace transform of fading, and also it is in log form. And it is easy to show that this L tilde function is indeed satisfying the conditions that we require, which are being non-negative, bounded, and non-increasing, if the original L satisfied these conditions.
It might be important to stress that this is conditional on phi, which is the amazing thing.
Yes.
It means that was whatever the realization you're sitting at the origin, whatever the realization of the point processor on you, that's a conditional phi, you see something which will be bounded above. And so, because I mean, this type of computation could be done just on average, right? But when it's conditional phi, this is the universality. So, like in network calculus, you will control the interference when you put this regulation at the origin, regardless of the configuration of points around you, right? And therefore, by the formulas which Ke showed, I mean, it will be universal. So you could put quantifiers everywhere in space. You will see the interference bounded above very constant. So the conditional phi looks innocuous, but it's
Yes.
it's a very strong statement.
Yeah, the conditioning on phi is the key element throughout this work, because it is what enables us to say something about all links of the stochastic model. So we have covered ball regulation and short noise regulation, and we have shown that they are equivalent, and they give some results about bounds of short noise and interference. The second class of regulation is called void regulation. We say that a stationary point process is strongly tau void regulated if you have a closed ball centered at the origin, and you count the number of points around you within radius tau, it is lower bounded by 1. What it means is that if you start from any location in R2, you can always say a point within certain radius. Any questions? So the physical meaning of this void regulation is related to the notion of coverage. For instance, in cellular and satellite network, it is to ensure that you have a strong enough link with a nearby transmitter. So similarly, by stationarity, we can show that for any location on the plane, you have this coverage or void regulation. And it can be generalized to our dimension, arbitrary dimension. And we have a much stronger result that says that it actually implies that all the locations on R2 satisfy this constraint simultaneously. Okay, we have covered the 3 regulations so far, and here are some properties related to these regulations that we have introduced. The first one is called superposition, where we have a set of stationary point processes defined on the same probability space. If each of the point process phi sub I is strongly ball regulated by some parameters, sigma I, rho I, mu I, then the superposition of the point processes is strongly Ball regulated. And if each of them is tau I void regulated, then the superposition is strongly void regulated as well, which is the parameter is the minimum of all the tau I. And the example is so we give an example earlier of hardcore point processes that satisfy this polynomial constraint. In fact, being hardcore is not the necessary condition, because by the superposition property, any finite superposition of hardcore point processes are still Ball regulated. So it is not necessary to have a minimum hardcore distance between points.
Just have a question about the void case. So you gave some example for the Ball case with the what you call, I do not remember the name of the process, the hardcore process, something like that. You didn't give some example for the void case. In fact, is for example the classical point process, post-harmonic process, is satisfy also the void. No.
This is a good question. The answer to the first question is yes, and to the second is no. So maybe I start with the second. The Poisson point process is not void regulated, because by this expression, you cannot almost surely upper bound this number or lower bound. But for instance, lattices where there are some rigid structure, they are tau void regulated. So square lattices, they are void regulated. Yeah. So it's also a good.
Just to have some examples. I wanted to have some example that of process that are void regulated or not. Thanks.
Yeah. Question.
It's very important later on for some architectures, but you've seen the result that Ke presented. So grid is of course both void regulated and
the grid is rigid.
Yes, but it's void regulated and it is Ball regulated for shortness. Matter, take Poisson, you materialize it by hardcoring, and you get also something which is only Ball regulated. But the superposition of grid plus matter will be both void regulated and Ball regulated. And so this superposition theorem are very important. You can construct them and solve them. Okay. Systematic.
Yes. So if you think about joint property of being Ball regulated and void regulated, you have four different cases of being Ball regulated and not void regulated, and vice versa. Yeah. So here, Martin hardcore point process are Ball regulated, but it's not void regulated.
Okay.
The second property is displacement. So we have an original point process and we add some vectors to each point to shift it in the space. If the random vectors v of x are bounded and stationary preserving, then phi tilde, which is the displaced version, is strongly Ball regulated if and only if the original point process is strongly Ball regulated. In fact, there are some more precise results, but it's not sure it will not be discussed here. And secondly, if phi tilde is strongly void regulated if and only if the original point process is strongly void regulated. It's actually not very hard to see this given the sphere packing example that we have, because if you have a bounded vector then the shifted version will be contained within some ball of a larger radius. And an example to this property is random translated lattices are ball regulated because lattices are ball regulated.
I'm sorry, I'm not sure I understood. Because if you take the x constant, you have a translation. It won't be, if the original one is not regulated, then the second one won't be, right? Maybe I misunderstood.
The first one is not regulated. Then the shifted version is not regulated. Is that the question?
Now, what you're saying is that displacement keep the regulation. This is what you're saying.
Yes.
Yeah, I'm sorry.
So, okay.
Sorry.
Some of you might be wondering, why do we use this polynomial form of constraints? Other than the fact that it is an analogy of the network calculus, the sigma rho regulation in network calculus in time extended to space. Well, in fact, it is not a necessary condition, necessary constraints. We have a generalized version for ball regulation. Because for some point processes, we know that there are better results for this upper bound on counting the number of points. And this example I give here is known by first by Gauss. It is to count the number of points within radius r from a square lattice. And it is a surprisingly difficult question, which has a conjecture that the number of points will deviate from its mean in a form of in a symptotic form of a square root of r, but it hasn't been proved yet. So this motivates us to define a generalized version, that is to shift from polynomial form to non-polynomial form. So our only requirements for G is that it is asymptotically R2, non-negative, non-decreasing, and it has only countable discontinuities. We say that a stationary point process is strongly G ball regulated if for all R larger than 0, the number of points within ball of radius R is upper bounded by this function G of R almost surely. So I give a quick example here, which is the floor function of the polynomial form. And we can show that we have an equivalence between G ball regulation and the short noise G short noise regulation, which is the inequality defined here.
Just a question here. What is the advantage to consider something that is flawed compared to the the function that is the original one? What is for me? There is only factor one indifference, maximum factor one indifference between the two. So what is the advantage to go to?
The advantage is when you want to have a bound as tight as possible.
Okay.
So if you want a very tight bound on the short noise, then we show that there exists. So it's not exactly in polynomial form.
Is to have bounds that are more tight.
Yeah.
Okay.
Okay. Okay, so coming back to the whole picture here, we have introduced the two types of regulations. And we will show shortly that this will give us service curves in wireless networks for all links. But before that, we will briefly touch on the two different senses of regulation, which are the strong sense and the weak sense. So all the previous definitions involve arbitrary location in R2. Now we introduce a second point process, which is the set of observers. Why? Because in many applications, the perspective of interest is only from a specific set of observers rather than an arbitrary location on the plane. For examples, when you have two set of transceivers, a primary set of transceivers and a secondary set of transceivers, the type of regulation that is mandated for the first type might be much stronger than the second type. So there will be a disparity of performance between the different types as well. The second example is when you have the coexistence of multiple network architectures, such as the coexistence of Wi-Fi and cellular in the unlicensed spectrum. And the tool that we use to introduce the weak spatial regulations is palm calculus. It is essentially conditioning on having a typical observer at certain location. Okay, so we have 2 point processes, phi and psi, which are defined on the same probability space. And we say that phi is G-ball regulated with respect to psi if for all radius r, observing from the conditioning on having a point of psi at the origin, it observes the number of points from phi is upward bounded by this function g of r. And the weak void regulation, weak short noise regulation are defined similarly by having this inequality for p sub psi of O almost surely rather than P almost surely. A special case is when the 2 point processes are independent from each other. And in this case, strong equals weak. Generally speaking, strong implies weak, and the converse is not true in general. We have a very detailed and more rigorous presentation of the strong versus weak relation. But I will skip for now. And just to point out that you can take the second set, which is the set of observers, to be the same as the point process being observed. So we come to the second part of the talk, which is to apply the techniques and regulations that we've introduced before to different types of wireless structures. And here we look at an example of the device-to-device network, where you have transmitter locations being modeled by a stationary and ergodic point process. Each of the transmitter has a dedicated receiver within a fixed distance, as shown by the figure here. It is oriented at a uniformly random direction. We call the receiver point process by psi, and it's easy to see that psi is a displaced version of phi. And by the displacement property, we immediately know that Bohr regulation of one will imply the other. And it's the same for void regulation. Any questions? Yes. Yes. Actually, all the point processes are void regulated. In this model, they're all weakly void regulated, because at any observer of the second point process, at the receiver point process, you always see at least one transmitter within radius call. Yeah. So it is.
It's all regulated with all.
Sorry.
It's all regulated with all the including things.
Yes. Yeah.
But the key thing is weak.
Yes.
And so you will see that later on in cellular also, it's so weak and strong are completely different. You are something way weaker indeed, and here it's guaranteed because of the type of.
Yeah.
But you could have absolutely no strong. So it's big voids, right? And so there are locus, there are location in space where you see nobody, but on the observer, it's guaranteed.
Yeah. A more extreme example is all point processes are void regulated with respect to itself. So always observe points for sure. Yeah.
He's a mathematician.
So we look at the typical receiver at the origin, and it has a dedicated transmitter at T, which is of distance tau.
I just have a question here. Is it realistic to such kind of hypothesis? Each receiver is at the same distance of the transmitter?
It's not exactly realistic, but you could have a range of distance. Yeah.
Range of distance.
It's a simplification for sure.
You can think, for example, of the vehicle devices inside the same vehicle that have to transmit to each other. It was mentioned.
I didn't have this example in mind.
Yeah, that's for example the probes to prevent using wires, too much wires in the car.
It's a good example.
Communicate with Wi-Fi or like.
Yes.
You can think of that.
Thanks for the addition. And we have small scale fading, which are marks at each transmitter. So h of x will be the fading from a transmitter point x to the typical receiver at O. And L is the path loss function, which naturally satisfy the constraints that we have earlier for the short noise regulation. The total received interference is h of x times L of x subtracted the only point that is the dedicated transmitter. And we define the link reliability to be the chance of success, which is when its SINR is above some predetermined transmission thresholds. Also, it's important to note that everything here is conditioning on phi. So what it means is that you associate something individually with each link. So it's like the figure on the left-hand side. And the ergodic channel rate is treating the interference as noise and looking at it in the very long term. Our first corollary, which is very immediate, that is, without fading, if the transmitter point process is more regulated with respect to psi, then the SNR is lower bounded by a deterministic quantity, almost surely. And a very important remark is that if phi is a Poisson point process, which is not Born regulated, then you have no lower bound for the SNR, even without fading. With fading, we go to the notion of reliability and ultra reliability. So if you recall this bounded Laplace transform that we obtained earlier, it will be used here to derive the reliability bounds here. The theorem says that if phi, the transmitted point process, is Born regulated with respect to psi, and the fading satisfies this Kramer condition, then for any transmitting threshold theta, the reliability is lower bounded by some deterministic function, which we call zeta of theta, and it is in computable form. So on the right-hand side is some simulation result. You can ignore the legends here for now. So the blue line is the simulated reliability, worst case reliability for different transmission threshold theta. And the red curve and the black curve are the two deterministic functions that we derived for this simulation scenario. You can see some gap, but it's a lower bound for the worst case bound. And the second theorem says that for any epsilon larger than 0, you can find some delta small enough such that an arbitrarily high reliability can be achieved for all links. It will correspond to the region of the figure where you have a horizontal line that is very close to 1. So this is in the context of ultra reliability for all links. And neither of the results are possible for Poisson type of networks. And similarly, we have for all links, there is a lower bound for the ergodic channel rate, whereas a Poisson point process will forbid such a lower bound. Lastly, we have shown that we use these regulations to give some performance guarantees for all links in a wireless network, and it is possible to combine this tool with the classical network calculus when there's a queuing element in the network. So if you consider a countable collection of queues associated with each of the link, and every queue has an infinite buffer with first input, first output scheduling. If the point process are regulated, then in the absence of fading, there is a region of traffic arrival such that the queue length is upper bounded deterministically, and the latency is also upper bounded at each queue. So this is a combination of the service curve, a deterministic service curve in the wireless setting with traffic constraints from the classical network calculus. And in the case of Kramer and ergodic fading, we have that if the traffic arrival rate is strictly less than some threshold rho star, then all the queues in the network are stable. Furthermore, the tail distribution of the latency and the queue length is also upper bounded. In contrast, if there's no such spatial regulation, then there is always a non-zero fraction of unstable queues. So I give the example of a device-to-device network model. We have similar conclusions for cellular models and ad hoc models, but due to the time limit, I will not cover them today. To summarize, we introduce spatial network calculus, which extends to space the theory of network calculus initially developed with respect to time. And we show that it is a necessary and sufficient condition for obtaining performance guarantees for all links in wireless networks. Lastly, it can be combined with the classical network calculus framework to have end-to-end latency guarantees and queuing length. That will be all. Thank you.
Thank you. Any question in the room?
So you mentioned the Poisson point process is not more regulated, but you have an example of beside hardcore process for the type, for example, determinator processes.
I have example where, in fact, there is a very fundamental way to define whether a point process is ball regulated or not. It is that any local, you could find local balls that is locally bounded. So any point process satisfying this condition will be ball regulated. Yeah. So the example that I have other than hardcore point processes and lattices are any superposition of any any ball regulated point process with any other point process. But no, they must be all ball regulated. Yeah.
First of all, thank you very much. Very interesting topic and a high quality talk presentation.
Thank you.
I have plenty of questions on the way that this could be applied, because there are plenty of ways it could, I think, directly to existing networks. So in many cases, for example, in cellular networks, you won't be able to have an arrival process of the devices that you can really control. But you could add an access control to the system, right?
Mm-hmm.
To turn off or not to accept some devices that will not be conform with the boundaries we are defining.
Yes.
So do you plan to work in the algorithms to build this admission control?
Not at the moment, but it's a very exciting direction.
Yeah, and on the other hand, it could be used to plan the systems that are going to be deployed. For example, in an industrial plant, where this type of solutions could be used to monitor different things. You can imagine that you use this for planning.
It's meant for it, yeah.
Sorry?
This is meant for that.
Right. That would be great, because as we all know, this is a key problem today that people are trying to solve.
Yes, yes. What's most exciting here is we have explicit computable bounds for these performances, and you could reverse engineer algorithm satisfy a predetermined bound. Yes.
But to elaborate on that, I think it's the two questions are, so let me start with the second, right? There are lots of heuristic ways. If you think, I mean, we worked with Daniel a long time in CSM-SCA. CSM-SCA tries to do it, right? But we have not seen in our 2006 paper, we have not seen that actually when you have hardcore exclusion, we put a second order Poisson approximation to compute interference, which gives the situation that you get no deterministic, but if there is no failing, when you have hardcore, you can guarantee something deterministic. Nobody apparently has seen that, which is quite And so, frequency reuse is also trying to do the same. I use this frequency, you have the base station nearby, you silence if I talk and you right. So these are heuristic ways. But there is something which is like network calculus, on which you can unify all these things in a single object, which will give deterministic or computable guarantees when there is failure. To get. So I share your view. I mean, there is a high potential to design algorithms which would extend CSMA and which would give guarantees of either the deterministic. If you are in a floor of a factory, you could in principle have some ideas of multipath, control failing, and go to deterministic guarantee. That's the thing. And it should lead to algorithms. It should lead to algorithms. But so what has been thought of as a heuristic so far can be made unified in a single framework. And this is the main main thread, right?
Some question on the bridge? In the room? So, thanks again.